Okay, so now we're going to the pseudo-organic chemistry passage, which is organic chemistry unit number 11, please. Okay, I just remembered, I forgot to mention, I put a web page. It's free and online that has a summary of the GAMSAT organic chemistry reaction mechanisms. I also made a video trying to explain the page to people because, you know, they like to ask a lot of R prime, R double prime, R triple prime questions for the GAMSAT. And so I try to give context to that. And it also, the reason I just thought of it is because it talks about, as well, how to make a hemiacetal and an acetal. And that's, of course, what previous problem had, and that's what the next passage will have. So, did I put the link down there? So I put the link on the page. Thought I put there. And there's the link for you to see. Okay. So Unit 11, questions 26 to 28. So this is, yeah, I put this down. Oh, first of all, I have to say this. Over 100 videos. I still can't believe it. It's unbelievable. I don't know what to say. But we just uploaded our 100th video in 1 year. 1 year, 100 videos on YouTube, giving all the work solutions to all ACER's practice questions and some other videos, all for GAMSAT, which is absolutely unbelievable. So anyway, so now this is the first time we are surpassing 100. That's what we're doing today. Okay, so Unit 11, questions 26 to 28. This is MRI. So of course, magnetic resonance imaging or nuclear magnetic resonance. It's called NMR. It's the real name of the device, but we have to change the name for medicine because patients didn't want to have anything nuclear to do with their brain. They're happy to get an MRI of their brain, but they don't want a nuclear magnetic resonance of the brain. Oh, that would be horrible. So anyway, this is an unbelievably incredible device, which has nothing to do with this passage. But, you know, I'm sure you've seen images. You go into this massive magnet, and get this, the magnet reorients all the nuclei in your body. Is that insane? All your nuclei in your body are reoriented to be in line with the magnet. And then the magnet lets go, boom. And then the nuclei return back to their native state. And in so doing, they release energy. And then the system is able to detect the energy coming from those atoms and molecules. And that's how you can see these very detailed images by changing the nuclear spin on all your atoms at the same time. Crazy. But anyway, so this just is another one of these classic ACER passages in which they give you rules that you've never heard of before, and then you just have to apply them. Now, it does require some knowledge, though. For example, you don't have a periodic table for the GAMSAT. They've never given one in the past. And so you have to have a sense of the periodic table. What are the trends in the periodic table? Where are the major elements in the periodic table? Sometimes they can ask a question that requires, you know, a comfortable knowledge of where those atoms are, you know. And so because of that, you know, you have to, you need to have a comfortable view of the periodic table. That means you've looked at it a few times, more than a few. Hopefully you've done enough problems so that it becomes second nature. So they give you the rules, and basically all the rules come down to the, I guess it's the second or third sentence about all nuclei that have an odd mass number exhibit NMR, and then they talk about even numbers, and you know, it all comes down to this. So, question 26. Of the three isotopes of hydrogen, now, just in the back of your mind, you should know that there's hydrogen, there's deuterium, and there's tritium. And you can see what deuterium and tritium look like because it's answer choice D. In answer choice D, you see hydrogen, you see deuterium, and you see tritium. And of course, we're going to find out what the difference is between these different types of hydrogen. Of course, they're they're different types of it's the same atom. These are just different isotopes of the atom. So it's the same number of protons because it's the number of protons that defines an element. Okay, so here's an atom, and the typical way to write it is that at the bottom here, we call this the, at the bottom here is what's called the Z value, and that's the atomic number. And as I said before, this is the number of protons, and this is what defines the element. As soon as you say a certain number of protons, that's the element. It's atomic number that. It doesn't matter what this is. This is what tells you what element it is. And then up here, we have the atomic mass. Now, you can hear this called so many different things. So they might say this is the mass number. Fine, take it. They might say it's the atomic mass number. Fine, and that's why you can put an A there. They might call it the AMU, atomic mass unit. It ends up being the same number. They could also give you the gram molecular weight, or the gram atomic weight in this situation. The gram atomic weight is essentially the same as the AMU. Now, you don't have to get into the details, but basically it comes down to this. It comes down to the fact that the AMU represents what it is for an atom. The molecular weight, or the molecular mass, you can call it either thing. The molecular weight or molecular mass, the number of grams per mole, that's what it is for a whole bunch of atoms. How many, you ask? 6.02 times 10 to the 23rd atoms. And it's Avogadro's number. So when you're talking about a reasonable number, you've got some grams you're talking about, because you need some grams to work in a chemistry lab. You can't work with 5 molecules plus 2 molecules. It's not going to work. So you need so many grams with so many grams. That's why you need Avogadro's number, so you can convert what's happening at the atomic or molecular level up to something where we live. If we were mice, Avogadro's number would be different. It would be a lower number, because we would want to work with smaller things. We're not mice, so yeah, Avogadro's number is pretty nice. So this is the setup. So the Q, so that's the hydrogen, for example, and we know hydrogen is atomic number 1, but you have to know that. So so you know where it is in the periodic table. It's the first element in the periodic table, and then they give you the different mass numbers. So we just need to find out, do these all follow the rules? Okay, because we have the one which is hydrogen 1, hydrogen 2, and hydrogen 3. Okay, so first let's try hydrogen 1. So in their rules, they say all nuclei that have odd mass numbers exhibit NMR. So odd mass numbers. So that immediately takes care of H1, which is hydrogen, because it has 1, it's odd, and it takes care of H3, which is tritium 3 for trits, I guess, and or tri. Okay, 3 for tri. So then hydrogen has 3, and so we know that tritium and hydrogen definitely will exhibit NMR. So now we're down to answer choices possible C or D. So we just need to evaluate deuterium, because it has a mass number of 2. So it doesn't abide by the first rule, because the first rule is all nuclei that have an odd mass number exhibit NMR. As do nuclei that have, we've got nuclei that have an even mass number, but odd atomic number. Oh, wow, we hit it. Deuterium has an even mass number, and it has an odd atomic number, which is the Z value, which they're not showing, but we know is 1, because it's atomic number 1 periodic table. So hydrogen, deuterium, tritium, they all abide by the rule, and so answer choice D is correct for number 26. So now number 27. Number 27 is a little bit impressive to me because it does tell you that you've got to do a lot of problems, practice problems before sitting the real GAMSAT. And the reason is so that you have a good sense of the periodic table. That's the key point. You need a good sense of the periodic table in order to answer a question like this. Not a perfect sense, but a good sense. Okay, so in which one of the following lists does NMR occur in all of the nuclei? Wow. You see, this is time consuming because, you know, you have to sort of assess what's going on, but it is time consuming and you just have to be efficient. So it's not just that they're asking you, do you know what to do? They're asking, do you know what to do? Can you be efficient about it? So answer choice A. A, the Q would be helium. Yes, I just added some extra. So the Q will be helium. We have up here that the mass number is 4, and then the Z value we need to know. So the second element of the periodic table is indeed helium. First being hydrogen, second being helium, third being lithium. Actually, you should know lithium because actually it's Trivial Pursuit. That's it. It's a Trivial Pursuit question. What's the first metal on the periodic table? It's lithium, number 3. So you'll feel so smart when that comes out. So helium is number 2 on the periodic table. So that's 4 and 2. Helium does not obey any of the rules. We're supposed to have an even mass an odd mass number to exhibit NMR. It doesn't have an odd mass number. It has an even mass number, but it needs to have an odd Z value. It does not have that. So wonderful. What a gift that the first element that we check does not have it. That means all of A is wrong. But just for fun, let's look at beryllium. Beryllium is the second one. I'll be honest with you. I don't think they believe. I don't think that ACER thinks you know the atomic number for beryllium. And that's why they give you helium first so that you can discount the rest. Because, come on, you don't know the atomic number for beryllium. Maybe you do. And if you do, fantastic. But it's rare to talk about beryllium. So beryllium number 4. And so it has even, and even it's out. Wrong. Oxygen. This you should know. You should know the gram molecular weight of oxygen, the AMU16. In advance, you should know that just because of the number of questions you do, not because you memorized it. And you should know that the atomic number for oxygen is atomic number 8, also just because of what you've done. So we have 16 over 8. Wrong again. Bah, no good. And then next we have sulfur. So sulfur is 32. Okay, I see somebody's written that the atomic weight of beryllium is 9, but it's not the atomic weight of the beryllium in this problem. The atomic weight of the beryllium in this problem is 8. If they put 9, now we have a discussion. Now it's then it would exhibit NMR because it follows the first rule, but they wrote 8. So this is some isotope of beryllium, and we have to deal with this isotope, and it's 8 over 4. So oxygen is 16 over 8, out of it. Sulfur, 32 over 16, so that's also out of it. Actually. Okay, so then you look at answer choice B. So we have helium, which is 3 over 2, or it has 3 on top. We don't even have to check that it's over. It has 3, it's odd, it's good to go. Fluorine has 19, phosphorus has 31, they both get good. The only question is nitrogen. Nitrogen has 14, even is not good, but if there's an odd Z value, we're happy. Nitrogen has 7, we're fine. I don't think they think you know what the atomic number for a fluorine or phosphorus is, but you didn't need to know that in order to properly solve this problem. We were able to see one of the answer choices in A is wrong, and if you look at answer choices C and D, you can quickly see wrong things. D has carbon 12. Carbon 12 is over 6. That's even over even. No, bang. And then answer choice C, you have 6 over 3. Okay, that's all right. carbon 15 over 6. 15 odd. Okay. You have oxygen is 18 over 8. So that's no good, because I don't think they think you know what potassium is, the atomic number of potassium. But they just made sure you had enough to be able to succeed. And so the answer 27 is B, but it does require some experience, some comfort with the periodic table. Yes, in terms of molecules to know, no, this may or may not freak you out. Chon PC, yes, that's the mnemonic. These 6 atoms represent 99% of your body. 6 atoms, 6 elements combining in marvelous ways, of course, to create your body. And it's carbon, hydrogen, oxygen, nitrogen, phosphorus, and carbon. Calcium. Calcium, which of course is mostly in your bone in form of something called a hydroxyapatite, which we would never be asked. So, until you get into macros, come on. So, yes, those are the absolute minimum elements to know. But the first 20 elements in the periodic table, it's a good idea to be comfortable with those. Okay, question number 28. The number of neutrons in the nucleus of an atom is always. So now we have to look at the number of neutrons. Okay, so the number of neutrons is this again. It's the top minus the bottom, and that gives us the number of neutrons. So this is what we're interested in. Now, it says, is it always odd or always even? Well, if you have, going by the rules again, all nuclei that have an odd mass number. So if you have an odd mass number, this is odd. If all nuclei are going to exhibit NMR with an odd mass number, that means the Z value can be odd or even, which means that the neutrons could be odd or even. Just because of the first rule, we know the neutrons can be odd or even. So the idea of always odd or always even is wrong. Answer choices A and B, not even to be discussed because of the first rule. We know it could be odd or even. Now, we have to figure out the second rule. As do all nuclei that have an even mass number. So if you have an even mass number, but odd atomic number. So if you have an even mass number and odd atomic number, so you have an even number, you subtract an odd number, what do you get? Odd or even? You have an even number, you subtract an odd number, that means you have to have an odd number, and if you're not sure, just take examples, 2 minus 1, you get 1. So you get an odd number as the result. So you get an odd number as a result if you start off with a mass number that is even, you have an odd atomic number, you get an odd neutrons. Now let's consider, if you have an odd mass number here, we know it exhibits whether this is even or odd. We know that as long as you have an odd one, even or odd, you're going to have, it's going to exhibit NMR. So let's start with that. We have odd mass number. If this is even, then we get an odd number, right? 3 minus 2 gives you 1. So if this is odd and this is even, we get an odd result. So that means an odd result, odd number of neutrons, takes place if the number of protons are even. And that's according, that utilizes the first rule. Okay, someone's saying they're confused about question number 26. Could you be specific? What about question 26? Is it the hydrogen, the deuterium, the tritium? What is it? Well, first of all, you don't have, ACER did not require you to memorize that these are isotopes. ACER did not require you to know that it's called deuterium or tritium. They did not require that. I'm just giving you a little background information. ACER gives you in the question itself, of the 3 isotopes of hydrogen, ACER suggesting by the question itself that they are presenting to you 3 isotopes of hydrogen. So that's not something that you needed to know ahead of time. They're giving you this information. Basically, they're saying, take these things. They're all H's, so they're all hydrogens. The only thing you need to know from prior knowledge is that hydrogen is atomic number 1. And that means the Z value is going to be 1. That's all you needed to know. Because this Q thing, they gave you in every instance. It's H, hydrogen. They gave you that. You don't even need to know the word. You could forget the word deuterium and tritium. It's H. They gave you H. They gave you 1, 2, and 3. So you need to know that Z is 1 in all these instances because the Z value defines the element and the element is hydrogen. So the Z value is always 1 when you see H. But this was changed 1, 2, 3. So they're just asking what happens when it changes 1, 2, 3. Well, when it's 1 and 3, the rule says all nuclei that have an odd mass number exhibit NMR. So when it's 1 and 3, we don't even have to do anything. We know. And when it's 2, then we have to check the second rule. Second rule says if there's an even mass number, which is 2, even at the top, it will exhibit NMR if there is an odd atomic number, number 1.